Tiny airborne particles, or aerosols, can cool by reflecting sunlight or warm by absorbing it. And they change clouds, too. That tug-of-war is captured in radiative forcing. In major climate assessments, aerosols remain the largest source of uncertainty in how much we're warming or cooling the planet. HARMONIA's mission is simple: make aerosol measurements consistent so decisions rely on solid evidence. Natural aerosols like desert dust and sea salt look stable on average, but climate shifts can move them. For example, analyses show increases in Saharan and Arabian dust in satellite records, linked to winds, soil moisture, and vegetation changes. Future climatic scenarios also show a possible increase. That matters because dust is a major light scattering and absorbing agent. On the human side, air quality rules have reduced aerosols across many regions since the 2000s, while in parts of the developing world, we saw rises and then plateaus. Typical long-term changes in aerosol optical depth, or AOD, are usually found a few hundredths per decade from -0.028 to -0.010 per decade, but regional patterns vary widely. Detecting such small shifts demands extremely careful, consistent data. Will human-made aerosols keep decreasing or level off as controls max out and economies evolve? Only long, homogeneous records can separate policy signals from noise and spot turning points early. To be sure that we can assess these tiny trends, we need to reduce uncertainties, but today, instrument accuracy and stability can be similar to the trend's magnitude. Why is this challenging? Firstly, different instruments and networks, AeroNet, GAW-PFR, and Skynet, all measure aerosols, but optics, wavelengths, field of view, and algorithms differ. Then, calibration and traceability. Sonar sky photometers are calibrated via Langley methods at pristine high-altitude sites and intercomparisons. Reference triads and WMO formulas target AOD uncertainties in the range of 0.005 to 0.02, depending on wavelength and air mass. Finally, algorithms for calculating AOD can differ. Cloud screening, gas corrections, slit function, and forward scattering treatments can shift AOD by hundredths, enough to mimic a decade-scale trend in most parts of the world, if not aligned. For example, AeroNet Level 2 AOD and GAW-PFR network typical uncertainty is about 0.01 to 0.02 for field instruments. Small, yes, but the same size as many trends, so homogenization is essential. To see long-term trends, we need long records that don't drift. But uncertainty grows with time. A climate record relies on instrument stability, and every handover to a new instrument adds another step of uncertainty. The biggest danger is a data gap. Break the chain and you risk losing the entire trend. In the short term, relative uncertainties are small, but over decades can add up, widening the uncertainty until they can hide or fake a trend. What continuity really means: no gaps, maintain spares, service schedules, and funded continuity. Overlap on purpose. Keep old and new sensors running together for months to measure the offset and remove it. Drift watch. Use reference sites and routine intercomparisons to catch instrument drift early. Version control. Log every algorithm change, keep old outputs, and reprocess the full time series. Traceability. Keep a clear calibration chain back to references. Store metadata and uncertainty budgets with the data. Harmonization. Merge networks with standard methods and tests so the combined record is consistent. In recent years, there are efforts towards linking AOD measurements with metrology and SI units through WMO and BIPM activities. This works when metrology and atmospheric chemistry and physics pull together. By expanding this targeted synergy and by treating continuity as a first-order requirement, we cut the uncertainty growth that comes with time. What HARMONIA does: builds common calibration chains, compares and aligns algorithms, and connects networks so data are traceable and comparable. Satellites give the global map of AOD, but their accuracy rides on ground truth. Aeronet, Skynet, and GAW-PFR are used as fiducial references to validate products from MODIS, VIIRS, and others. Many teams literally treat Aeronet AOD as ground truth and validation because its uncertainty is well characterized. If ground networks disagree by 0.01 to 0.02 AOD, those differences propagate into satellite algorithms, bias maps, and trend estimates. Traceability efforts are crucial. Linking calibration to SI units and harmonizing Aeronet PFR tighten the entire chain from ground to orbit. These practices also improve downstream applications, air quality services, solar power forecasting, and aviation hazard detection. Some suggest solar radiation modification with stratospheric aerosol injection, putting reflective particles in the stratosphere to cool the planet and balance the greenhouse effect. Research warns of serious risks such as weaker monsoons in Asia and West Africa, changes in stratospheric ozone. Also, moral trade-offs should be considered, since cooling could be uneven and would affect agriculture and mitigation policies could be underestimated. Consequently, investigation of possible SAI effects requires high accuracy in the aerosol load and characteristics used in the process. Aerosols are tiny, but how we measure them carries huge consequences. By homogenizing data across networks, HARMONIA turns uncertainty into actionable evidence for climate strategies, healthier air, reliable energy, and safer skies.